All right, good afternoon, everybody. We are starting week 6 in algebra today. Also starting the third of 3 units that we have to do this term. A lot of threes there all of a sudden because we have 3 more weeks to get this all done, complete the final. Grades have to go in by no later than Friday, June 4th. So the final will probably be that Tuesday or right after Memorial Day. So more close to today is just a quick reminder about our little drive-through recognition thing that we're doing on Friday, right here at the Excel Center. You can drive through the parking lot, pick up some free food if you like hot dogs. I don't know what else is going to be given out, but it's been being done to sort of thank everybody for sticking it out and getting to this point in the term, and maybe give you a little boost to get finished since we are getting short on time. It's good, and not only just close to the end of the term, but close to the whole school year. So everybody will get off for summer break. And so 12 to 1 o'clock on Friday, that's the big event. So don't even have to get out of your cars if you don't want to. Just come on through the parking lot and we'll throw the hot dogs in there with you. Just kidding. I don't know how that's going to be done. So this third unit, this new unit we're starting today is about systems of equations. Anybody know anything about systems of equations? You hate it?
No.
Oh,
That's what
Jaden.
I hated that. And the Pythagorean theorem.
Okay, well that's geometry. I'll give you a break on that.
Algebra.
You did?
Pythagorean theorem.
Huh.
I learned it in Algebra 1.
Okay.
Freshman year.
It's a formula, so it's an equation. Well, systems of equations are just the same thing that we've been doing, except now it's 2 equations working together. And so we have to learn how to find one answer that works for both equations. Several different ways, different solution techniques that we're going to learn. Graphing is one of them. That's the easy one. Graphs just like all the other assignments we've been doing with graphing. Then we'll have something called elimination, which is my favorite because it helps you get out of standard form and allows you to do some cancellation. And then the third technique is called substitution. You've already seen in a lot of different situations where substitution comes in. This one's a little bit more extensive because now we're talking about taking something out of one equation and substituting it into another one, and then being able to finish the calculations based on that substitution. No big deal. It's just more of the same, twice as much. I can tell how everyone's so excited everyone is here in the room. So I understand it's been a long school year. You're almost done. So don't give up the ghost now. You still got a few weeks to recover if you're struggling. And so be sure you send me a text if you need some extra help. So the first thing we're going to look at is kind of an introduction. What does it really mean when we're talking about systems of equations? Thing we got to be able to learn how to do is figure out why these linear systems work the way that they do. Can we uncover what the solution is? Is there possibly more than one solution? Or is there no solution? Because it is possible that we can have no solution on some of these systems problems. The classic example of a no solution problem is when you have equations that represent parallel lines. The whole thing about these systems of equations is that in order to be considered a solution, they have to have things in common. So some solutions are going to be obvious. The place where two lines cross, for instance, that one point, that ordered pair is going to satisfy both equations. So those are the three options. We've talked about solutions in a lot of different ways. With inequalities, we've talked about solution set, a whole range of area that's on the graph. So it's not just one number. For a simple one variable equation, typically it's going to be one solution. Now we've seen some equations where there is no solution. In other words, if we lose all the variables get canceled out and we end up with something at the end that's not true. That's no solution. It's going to look a little bit different here with the systems because now we're talking about two lines on the same that get graphed together. We know what a graph is. We've been doing that now for 2 or 3 weeks. We're primarily going to be dealing with these systems problems in slope-intercept form if we're talking about graphing. That's no different than what we've been doing. We've tried to say, okay, regardless of what form your equation is in, if it's in standard form, let's try to convert it to slope-intercept, solve it for y. If it's in point slope, we can do the same thing there. We can solve it for y. Because that slope-intercept form is the easiest one for us to graph. Where do we start? We start with b. Every slope-intercept equation, we have to know what the slope is, and we have to know what b is. That's the y-intercept. That's why it's called slope-intercept. We have to have those two things because those are what we're going to use to be able to graph it. We start at the y-intercept. With these graphs here, y equals 3 over 2x minus 5. And if some of you that haven't done the Unit 2 test yet, this actually might help you. Because the Unit 2 test has been released, and you need to be sure that you understand how to identify the slope, which is m, and the y-intercept, which is b, the number that's in the position where b is. You also have to be sure that you graph your lines in the correct orientation. Positive slope lines go up and to the right. So this first one is going to go up to the right. The second one is going to go up to the left. If you have those notes where we did the 4 graphs of the 4 types of slope, and you're working on graphing, keep that on the desk in front of you. And I don't even care what assignment you're working on, you need to pay attention to that. And that's why these first 4 graphs are being shown to you again. Because what do we got? When we have these graphs, I'm going to start at -5 and go up 3 and over 2 to the right. And there's my line. That is a positive slope line. You should not at this point be graphing these kind of lines up and to the left. That would be a negative slope line, like you'll see in the second example. Remember, there's only 4 types of slope. This one I'm starting at 4, and I'm going to have to go down 6 and to the right 5 because I can't go up. I'll be off the graph. Down 6 to the right 5. The y-intercept is right there at 4 where the line goes through the y-axis. That line is going up and to the left. It's a negative slope line. What about these 2 examples? I'm still seeing people getting these mixed up too. First one says y equals -4. The second one says x equals 2. So where does y equal -4? Well, that's down here. The y-axis is down here. This is the y-axis, so I go to where it says -4. And I can put the line straight across. Because that's the line for y equals -4. So what's the slope of that line?
0.
0. Yeah. Perfectly flat line. Horizontal line has no slope. No rise. 0 slope. So if this first one is a flat line based on y equaling some number, where's the second one going to go? X equals 2. Right here is where x equals 2.
Up and down.
Yep. Every point where that says x equals 2 satisfies that equation. And what's the slope on that one?
Undefined.
Undefined, right. So right there in these first 4 examples are the 4 types of slope: positive, negative, 0, and undefined. Practice these, practice these, practice these. Make sure you know what they should look like based solely on the slope. Because that's what determines if it's going in a positive or negative direction. Negative slope goes in a negative direction, up to the left. Questions? Anybody? Okay, since we're talking about systems, there's a little piece here on the vocabulary. It says a system of linear equations has 2 or more linear equations. Well, thankfully, we're only dealing with 2. There are more complex problems that have more than 2. If you're concerned about how to use the word system or systematic or systematized, they all mean something a little bit different. Librarian plan to systematize the donated magazines. Well, that just means that she's going to create a system. How do you find the donated magazines? Well, that's what the librarian's got to figure out. The American system of government is based on the Constitution. Now, that's pretty obvious. Sam was systematic in his approach to studying for his final exam. Systematic means you have a routine. You have habits that you follow. You go step by step. But we're talking about a system. A system of linear equations might consist of two equations. Here's where you have the differences in the types of solutions. Now, don't worry about these terms down here at the bottom: independent, inconsistent, dependent. We're not going to worry about that too much. In fact, there's a typo I just saw on that slide. It's not just two solutions, it's infinite solutions. We can have 0, we can have 1, or we can have infinite solutions. The solution of a system means any point on each line that satisfies both equations. It's both, boss. And here's the graph, what the graphs look like. A system with one solution is that first graph. It's where two lines intersect. It's the x, y coordinates that mathematically solves both equations. Infinitely many, I'll come back to that in a minute. No solutions, though. On the right there, you can see parallel lines. Parallel lines will never cross. They have nothing in common. So how can you tell, even without graphing, how can we tell if we have a system that involves parallel lines just from the equations? How can we tell? We just did parallel and perpendicular. Same slope. All you got to look at is the slope. If the slope is the same in both equations, they're parallel lines. It's no solution because there's nothing in common. They don't share any points whatsoever. Now this middle one, the same, what's shown as the same line and infinitely many solutions, is a little bit different. It looks like one line. Well, how can that be? Okay, so here's one equation. Y equals negative 3x minus 12. Okay, that's a linear equation in slope-intercept form. I know the slope is negative 3. I know the y-intercept is negative 12. Let me see. Now, here's a second equation. That's in standard form. If this is a system, we got to consider both of these equations together. And what do we do with the standard form equation? Convert. Solve for y. Because we don't know what kind of solution we have for this system because our equations are in two different forms. So 6x plus 2y equals negative 20, whoops, not 1, negative 24. Okay. If I solve for y, I'm going to subtract 6x. This is opposite operation here. Not just subtracting 6, I'm subtracting. Nobody has seen this but me right now. Why is that? Hang on just a moment. All right, okay. Got that on the screen now. Sorry about that. So I'm converting this second one to put it in slope-intercept form. My x terms cancel when I use the opposite sign. If all I'm doing is getting rid of it on one side to move it on the other, I'm just using the opposite sign, because that's a positive 6x being combined with a negative 6x gives me 0x. That's what I want. I had to get rid of that x term. So the next line gives me 2y equals negative 6x minus 24. Not quite done yet. They still don't look like the same equation. So I got to divide everything by 2. Because now my opposite is I'm dividing everything by 2 here because that's 2 times y. Same thing on this side. Dividing both of these, all 3 terms by 2. And what do I end up with? Y equals negative 3x minus 12. Isn't that what I started with? Now, if you just look at those 2 equations to begin with, you don't know that they're the same line. You have no idea. And that is the situation that you get when we're talking about infinite solutions. That looks like the same line once you graph them, but you might not know it initially because maybe the equations are in different forms. So you have to put them in the same form before you're going to realize, hey, this is 2 different ways of saying the same thing. It's one line laying right over the top of the other. They have every point in common. So that's why there's infinitely many solutions for that situation. Focus question number 1. What's the solution for this system? We don't have any equations. We don't know where these lines came from. Doesn't matter. But you can see that they cross. So what is the solution to this system? What does it mean? What is it shown on this graph? Where do they cross? Two, negative 2, negative 2. We still have to do the ordered pair in the correct order. X first, Y second. To the right 2, down 2. That is 2, negative 2. That big red dot there where these 2 lines cross, that is the one point that satisfies both of those equations. That is a one solution system. Most of the time, that's what we're going to be dealing with. One solution that works for both. How many solutions are there for this system? 0. No solutions. That's right. Here we don't have the equations either, but graphically you can see that they're parallel lines. They never cross. They have nothing in common. Therefore, there's no solution. Last example isn't a very good one, really. It's intending to show the infinite solution situation. It's best displayed, in my opinion, if you have different colors, where you can show one line graphed directly on top of the other. And most of the time, that's because you start off with the equations are in different formats. like I did on the whiteboard just a minute ago. Questions, anybody? All right, be able to do these problems like nobody's business. So at the start of class, I mentioned there are 3 different ways that we're going to learn how to solve systems of equations, and graphing is the first one. If we have 2 equations that are both in slope-intercept form, like these 2 here are, we got y equals 2x plus 4 and y equals x plus 2. Those are easy to graph. Which one of those is the black line and which one is the red line?
The first one.
The black line is the first one. Very good. Thank you. That's Sama?
Esma.
Esma. Okay, great. Thank you. Now, how do we determine that? We just use the equation. We match it up with the y-intercept. Okay, the y-intercept is 4. Slope is positive 2 up 2 over 1. The other one has a y-intercept of 2. The slope is 1, positive. You wouldn't think necessarily the 2 lines going in a positive direction would ever cross. But because slope is a measurement of steepness, they can cross about anywhere. And so which of these points here in number 11 is the solution for that system? You got 4 different points that are shown here: 2, 0, 0, 2, -2, 0, and -2, 2. Which one of those points is the solution for that system?
-2, 0.
-2, 0. -2, -2 is down here. That's not even on either one of the lines. The solution is the intersecting point. It's the one point that both lines share. So all you have to do is find that spot on the graph and identify the coordinates for it. We're going left 2. We're at the point of intersection. We don't have to go up or down at all. So the x value, we move 2 to the left, so that's got to be -2, but we're not moving up or down at all, so the y value has to be 0. We're sitting right on the x-axis. Any point that's on the x-axis is always going to have a y value of 0. So underneath those 4 points, it says check your answer makes both equations true. What does that mean? What if we didn't have the graph? What if we couldn't look at it? Well, we still need to be able to verify our answer somehow. And this is another form. This is another way to do substitution, kind of like you did substitution in order to find the y-intercept. We're going to take our x and our y value, and we're going to put it in the equation and see if we get a true statement. So the y value is 2. Put it in this first box. The x value is -2. Put it in the second box. So we're trying to figure out if the left side is going to be equal to the right side. So 2 times -2 is -4. -4 plus 4 is 0. So 0 does equal 0. Great, works for the first one. What about the second equation? Same substitutions. 0 from the point is y. -2 from the point is x. 0 equals -2 plus 2. Yep. Negative 2 plus 2 is also 0. Now we verified it. So if you're ever unsure, if you think, well, maybe I got this graph wrong, that's how you can check your work. Plug those points back into the equations, and it has to work for both of them. It can't just work for one and not the other. Because you're going to see problems where it's going to ask you, is such and such a point a solution to these two equations? So how are you going to figure that out? Are you going to graph it? Are you going to check it mathematically like I just did? Are you going to do elimination or substitution? You have options, and it really depends on what you prefer to do, what you like to do best. Questions on that, anybody? Okay. So here are two equations. Now, even before doing a graph, it probably makes sense that it would be obvious that these two equations are going to result in crossing lines, because we have one with a positive slope and one with a negative slope. So one's going one direction, the other's going the other. They're going to have to cross somewhere. So which line is the black line? Which equation is the black line?
The black lines first one.
Yep. Again, the easy way to identify it is start with the y-intercept, because you know that that's a point on the line. It's where the line crosses the y-axis. So if you can verify the y-intercept, they don't have the same y-intercept, so they should look different. They should be at a different place on the graph. And these are. We got one here that crosses at positive 4. Okay, and then I'm going to verify the slope, up 1 over 2, positive, up 1, 2 to the right. Yep. The other one, the y-intercept is at 1. And if you do that, it's no different than when you were graphing an individual line. The thing about graphing the slope intercept now, though, in these systems is you have to be precise. A sloppy graph is going to lead you to a wrong answer, especially for these kind of systems where you have only one solution. So my slope on the second equation is negative 1/4. So I'm going up 1, 4 to the left. 1, 2, 3, 4. Now I'm sitting on both lines. If I came from the other point, left, excuse me, down 1, left 2, down 1, left 2, I'm back at the same point. So I'm pretty confident that that point, negative 4, 2, is the solution for both equations. Pretty confident I got it graphed correctly. And I'm being precise. These are the kind of problems where you probably should try using a ruler, because the solutions that we're looking for are typically not going to be in between whole numbers. They're not going to be fractions. They're not going to be decimals. They're going to be sitting right at a graphing intersection where we have whole numbers. Question, anybody? So here's two equations, another system. What's the solution for this one?
No solution.
No solution. Correct. No solution. I've graphed. These both have been graphed. Here's the this one here with a y-intercept of negative 4 is way down here, up 6 over 1. The other one, positive 3, that's this line. What do you notice about the equations?
Same slope.
Yeah, same slope. Don't even need the graph. If you notice, same slope on a system of equations problem, automatically that's going to tell you that the lines are parallel. Because that's the rule for parallel lines, same slope. The only difference is going to be the y-intercept. Okay, here's one. If you got some graph paper, I'm going to pause the recording here, give you guys a chance to try to play with this a little bit. If you're here in class, I do have graph paper if you want to use some. And I'll pause this recording. I got an answer of -4, 2. You got this line, the first line going in this direction up to the left, the second line going the opposite way. And the coordinates where they cross, -4, 2. Anybody get anything different than that out there? Okay. Now here's a focus question that's already been solved. Y equals 3 and y equals x minus 1. It's a good one to practice the recognition of this horizontal line here at y equals 3. Remember, every horizontal line is going to cross the y-axis at a number, and that is going to be the equation for that whole line. Y equals 3. Every point on that line has a y value of 3. That's actually an easy one to come up with a solution because it's flat. So what you're really looking for is to get the other line on here graphed correctly to find that crossing point. When in that second equation, when we have a slope of 1, it's a perfectly diagonal line. Up 1 over 1, up 1 over 1. All the way up until you hit this other line at the point 4, 3. And if you look down here under step 3, where it says the solution or the answer, 4, 3. Step 4 would be to check it mathematically like I did on the last one. Well, it's pretty easy when you got y equals 3 as one of your equations, because what's the y value in our solution? Y equals 3, right? Sorry. Any questions? Anybody got questions on that focus question 4? Now number 5 is getting a little tougher. Now we've got 2 standard form equations. I don't know what we have. 5x plus 2y equals -4. X minus 2y equals -8. Well, they're probably not the same slope. I don't think they're going to be parallel, even just looking at the equations. If you look over here in step 1, it says make sure both equations are in slope-intercept form. Okay. So that first one, does everybody remember how to translate these, to convert these into slope-intercept form? Does anybody not remember? Okay, Kaleo, if I said solve those for y, would you know what to do? Okay, I got my two equations that are in that systems problem. They're both in standard form. I was asking if people understood how to convert them to slope-intercept. And what is slope-intercept? Y equals mx plus b. What does slope-intercept start with? It starts with y. So converting the other two equations means we got to get everything from the left side that's not y over to the right side. Cancel it, eliminate it, divide it, subtract it. We got to do something with it and end up with only y on the left. So the first thing you're going to do in every case converting standard form is to deal with this. Because we're solving for y. We just want to leave the y term where it is. So how do I get rid of that 5x? It's not just 5. I'm not just subtracting 5. I'm subtracting 5x. I'm actually not even, in my mind, I'm not even subtracting. This is a positive 5x. I'm canceling it with a negative 5x. It's the same thing. It's just a different way of looking at it. If you, like you guys have heard me say before, if you get stuck in adding and subtracting, algebra is going to be hard. Think about these in terms of positives and negatives. Every term is either positive or negative. You can offset a positive term with a negative term and vice versa. We can cancel with positives and negatives. That's all we're doing here. We're getting rid of it on the left side. And we got to do that on both of these because that's a positive x on the other one. This is remember, this is from the last unit. So if you struggled with this or if you didn't do well with it on the test in unit 2 on the test, this will help you. So now our x terms are canceled. And because I know I'm going to slope-intercept form, I'm putting the x term in immediately after the equal sign. Negative x minus 8. Okay, now what? Yep. I'm trying to get these both into slope-intercept form. I've canceled the x term, got it moved to the right-hand side. Now what do I do? By what? Yeah. Divide everything by 2. Not just the 2y. Remember the golden rule. If you do something to any term on the left side, you have to do the same thing to every term on the right side. It's the whole balancing issue. Because if I only divide that term there by 2, or in the other one, I'm dividing by the, remember, we're talking about division by that coefficient. Another one of those vocabulary words. The coefficient of y is what we're actually dividing by. If all I do is just divide that term, I'm not even anywhere near close to solving this problem. And now I have an out of balance problem. But as long as I do the same thing to every term, now I'm staying in balance. So I end up with y equals negative 5 over 2x, 4 divided by 2 is 2. It's negative. On the second one, I get y equals, and I'm going to put a 1 here to make sure it's easy to see that that's negative 1/2 x. 8 divided by 2 is 4, and that's also negative. Every standard form equation gets converted to slope-intercept in exactly the same way. And you got to remember, the problem with standard form is that we don't have the slope, so we can't evaluate whether or not something is where the two lines are parallel because we don't know what the slope is, so we can't compare them. And we don't know what the y-intercept is, so it makes it harder to graph. But now I got these two equations converted. 5 over 2x minus 2 and y equals negative 1/2 x minus 4. Now this seems kind of weird too, because now I've got two different equations, both with negative slopes, and they're going to have a uh-oh. I have made a mistake. Where's my mistake? Look at what I did over here. I forgot the minus sign.
Mm.
Ouch. So what I just said about two lines with negative slopes was incorrect because I didn't follow through with that -2 division. I forgot the minus sign when I got to the right-hand side. So these actually now change to be positive. That one becomes positive 1/2 slope with a positive 4 y-intercept. And while I was doing it, it didn't trigger that that would be the case. So what do you think it was that caused me to realize I had something wrong? Say that again. Which, there's two lines. Which one? The one going up to the right? Yeah, that tells me right there that that one's positive. Right, exactly. Because what I was expecting when I said I got two negative slope lines is that for them both to be going up and to the left somewhere. And so I realized at that point I had done something wrong. It's going to sound like a broken record, but it's always the minus sign. It's the negatives that mess us up. That's where most of our mistakes come from. So we got a solution that's a little bit more obvious now that we got the slopes correct of -2. So it's left 2, then up 3. That gets us to the point where those two lines cross. Now you could still do the calculation to verify that that is correct by substituting it back into those standard form equations if you wanted to. Not necessary, but you could do that. In fact, in this case, because I made a mistake on the slope, I might go ahead and do that calculation to be sure I got it correct. Because if I graphed it the other way and then I did the calculation, I would have found out by calculating that I had the wrong answer. And that would have caused me to go back and look at my earlier work. If I didn't have the graph and all I was doing the calculation, I would have figured it out eventually. So that's one of the benefits of doing that substitution to check your work. Step 4, check your answer by inserting the ordered pair into both of the equations to make sure they're equal. Questions, anyone? All right. So one of the things that you'll see in the materials for this, the start of this unit, is a couple of these PDF files. And I would encourage you to download these or print these out and do some practice with these. There are several benefits to that. Number one, you'll get plenty of practice graphing slope-intercept equations because now you're going to have 2 to do on every graph. And secondly, it never hurts to get some graphing practice. Forces you to think about the y-intercepts, forces you to think about the slope. Is it going up to the left? Is it going up to the right? Whatever the case may be. Now, if you look at those first 2 examples that I got on the screen here, how many solutions are we talking about for those? Can you estimate? 2 for each or 2 total? 2 for each? How do you get 2? Okay, but remember, there's only 3 possibilities. 1 solution, no solution, infinite solutions. Those are your only answer choices for that question. How many solutions? It's either 1, none, or infinite. 2 is not even possible. So if you see a question on the test that asks you how many solutions are possible in a systems of equation problem, those are your 3 answers. 1 solution, no solution, infinite solutions. These first 2 have a mixture of positive and negative signs on the slope. So they are going to cross somewhere. Those are both going to be 1 solution graphs. Same with the next 2, 3 and 4. Don't see any that have the same slope. Even the ones in number 4 that have a bunch of negatives in them, well, okay. For this first part of number 4, y equals -1 just goes straight across here at -1. That's a horizontal line, one of those special case lines. This one starts at +4 and is going to go that direction. So it's going to cross that -1 line on y here somewhere. So those are going to be 1 solution problems. Same with number 5. You got 1 positive slope, 1 negative slope. They are going to cross somewhere. What about number 6? No solutions, right? Good. Now you're getting it. And we haven't graphed anything yet. But what I'm trying to get you to think about is what, this part of algebra with all this graphing is very visual. So if you can visualize what your answer might end up looking like, you're already a step ahead of the game. Well, here we've been talking about parallel lines having the same slope already for like 3 weeks now. So now you have the extra piece of information that parallel lines in a system have no solution. So, okay, these both have the same slope, which means they're parallel, which means this is a no solution system because they never cross. They're both going to go up and to the left. One's going to cross here at -2. The other one's going to cross, +2. The other one's going to cross at -2. Up 2 over 1, up 2 over 1. They're both going to go that direction, up and out to the left. No solution. What about 7 or 8? One solution in each. Yep. Don't have any that have the same slope. They're all in slope intercept, so that's helpful because we can see the slope on all of them. See, the other advantage of having you guys print these out, and you know, if you want a hard copy, I can print it out here to do the practice. If you look at the solutions that you're given on the 3rd and the 4th page, if you don't peek and you do the practice, now you got something to check your work against, the correct answer. And then you can do an actual comparison. Well, the correct answer looks like this. What did I do differently because I didn't get the same answer? That should be, as a strategy, that's a good approach for anybody studying math. If you got the right answer, okay, how do you know it's correct? If you got a different answer, then analyze what you did so you can determine what you did wrong. So here's the no solution problem. Clearly parallel railroad track like type thing. The ones with the negative slope are interesting, number 7, because they don't cross until they get way down here in the corner. That's just the luck of the draw. That's just the way that it goes. Question, anybody? Sure. Now, this is another one of the handouts that is included in the materials that you have in Google Classroom. This one is taking another step beyond, and we'll get into more of the other types of solutions on Thursday. So you've got some graphing examples, and they've taken the extra step here to include some that are in standard form. So you're going to have to do the conversion first. Then here's what we're going to get into on Thursday: solving by substitution or solving by elimination. I don't want to start that today because it's way too involved to get into with less than 10 minutes left for the period. But that's what we'll be doing next. Although there are some different graph examples on here that you could play with. And we've got plenty. I've got as many examples of these as you want. I can print out for you. Graphing, substitution, elimination. This is one that we'll probably do together in class where we get some of these other examples done. And it looks like I need to upload it into Google Docs though, so I'll try to do that today. So questions, anybody? That's probably a good stopping point for today. Okay, well, appreciate everybody being here today. Be sure and text me if you want to set up some extra time for help. We have to schedule those. And don't forget about the drive-through free lunch on Friday here. Come get some hot dogs or whatever. Questions, anybody?
No.
No, thank you.
All right. Thanks, y'all. And we are out of here for today.